In these last couple of pages, we'll look at some examples of hypothesis testing for difference data, both if we're given the summary statistics and not. So let's hop into this example that we've been working with. We've got 200 observations were randomly sampled from a recent SAT reading and writing tests. The same students took a reading and writing test as are shown below. So we've got our student number, and then their reading score, and then their writing score. And first thing we'd want to make sure of is, are we working with paired data or independent data? Obviously, we've talked about this up until this point, but we wouldn't want to compare student number 1's reading score with student number 2's writing score. We're trying to compare each student's reading score and writing score, and that's what tells me that this is paired data. So, continuing on, it says the observed average difference between the two scores is negative 0.545. So before I do anything else, I'm just going to make a note of that number. It says the average difference between these two. So this means the average difference, the population, not the population difference. This is actually the sample mean difference or the sample average difference. So x bar sub d is negative 0.545 since we're talking about a sample. And then the standard deviation of the difference is 8.887. So the standard deviation, I should say the sample standard deviation of the differences is 8.887. These numbers will certainly come in handy for us as we're working our way through the problem. We would like to test the claim that there is a difference between the average reading and writing scores using a significance level of alpha equals 0.05. We'll obviously be using that number when we come back to make our decision. So first step, as always, is we want to talk about what's our null hypothesis and what's our alternative hypothesis. So what is H naught and what is HA? And if we can make the determination at the beginning of this problem that this is going to be for paired data, we're testing for paired data, then that means that the null hypothesis we sort of always get for free. It's always assumed that the mean of the differences is equal to 0, meaning that there is no difference, right? We could also write this out, again, if you want to make sure you know the order of subtraction, because sometimes it would matter particularly if we're doing a one-tailed test or we're trying to make the claim that one of these scores is higher than the other. Then we would want to say, okay, the mean of the reading scores minus the mean of the writing scores is equal to 0, something along those lines. In this case, it doesn't matter too much, though, because it just says, is there a difference? We're not claiming that one is higher than the other necessarily. We just want to know, are they different from each other, which means that when we come to talk about our alternative hypothesis, the alternative hypothesis will be that the population mean of the differences is not equal to 0, meaning that when I subtract these two, when I take the mean reading score minus the mean writing score, I'll just get something that's not 0, meaning I'm subtracting two different numbers. So, okay, we've got our null hypothesis, we've got our alternative hypothesis. The other thing that we would want to do here is just make a note of any summary statistics that we've had, and in this case, that's what we have already gathered from our problem. We've gathered our x bar and our S, our sample standard deviation. I'm actually just going to bring that down because we are certainly going to be using that in our next few steps. So then other thing I guess we'll mention real quick here is that we want to make sure we know our sample size. We had 200 students, which means that n is equal to 200 for this problem. All right, moving on then to our second step right here. It says, all right, check our assumptions and conditions. Do we have independent random sampling? In this case, yes, we do. We've got a random sample, and then we would want to check our conditions. N is equal to 200, which is certainly greater than or equal to 30, so that means, hey, we're good to go. That means the central limit theorem works, and we're good to go for this problem. So at this point, step 3, we would say go find the mean of the difference data and the standard deviation of the difference data, but this problem, already gave that to us. That's what we would be looking for right here. In some cases, we may need to use our graphing calculator to do that, in which case that's fine. That would just be an extra step. However, this problem just gave that to us, so that's great news. So then what we have left to do now, we're going to go and do some calculations at this point. So we're going to start off our calculations. We want to find our standard error. So standard error is the standard deviation S sub d divided by the square root of n. And you'll notice again that these formulas are very, very, very similar to the formulas that we used for one population mean. And that's actually kind of what we're trying to do, is we're trying to kind of combine these two data sets into one, and we can only do that because we're working with paired data. So my sample standard deviation was 8.887 divided by the square root of 200. So let me go ahead and calculate that out real quick. 8.887 divided by square root of 200. I ended up with 0.628. I'm going to go ahead and round to 3 decimal places here. Once I've got my standard error, I can go ahead and find my test statistic. So a test statistic is going to be a t-score. Remember, we're using our t-distribution because we're working with population means. And for that, I want x bar sub d divided by my standard error that I just found right here. So I want x bar sub d, and really what I should be doing here is it's always your point estimate, which is this guy, x bar sub d, minus the null value. But if you'll notice up here, the null value, the number that we talk about in our null and alternative hypothesis, is just 0. So I really should be saying minus 0 right here, but of course subtracting 0 doesn't do anything to that number. So you'll oftentimes see that part just left out as x bar sub d divided by our standard error. So if I do that, x bar sub d is negative 0.545. Our problem gave that to us, divided by 0.628. So let me go ahead and divide that out. Negative 0.545 divided by 0.628. I ended up with negative 0.868 if I round to 3 decimal places. Remember that this is a t-score right here. And then the other piece of information that we're going to need is we need to know our degrees of freedom. So degrees of freedom, remember, simply just n minus 1. So our degrees of freedom in this case would be 200 minus 1, or 199. So the numbers that I'm most interested in right now to go estimate my p-value then are the test statistic, negative 0.868, and my degrees of freedom, 199. I'm going to need those two numbers to go find my p-value. So next step, I need to hop over to my t-table at this point, and I'll say, okay, we'll hop over to our t-table. And let's erase just so that we don't get mixed up looking at this. And actually, we're going to need a higher degrees of freedom. We're going to be looking down here. So we said in this case, our degrees of freedom was 199, and our test statistic t was equal to negative 0.868. So first of all, let's talk about degrees of freedom. You'll notice that 199 does not appear here, so we have to go down to the next highest degrees of freedom, which means we're looking at this row with 150 degrees of freedom. So we are looking at that right there. My test statistic is t equals negative 0.868. Remember, our table doesn't show us negative test statistics, but we can just go ahead and change the sign to positive 0.868. And then I'm going to look for where that test statistic lives in my table. And in this case, it's smaller than or less than all of the numbers that I've highlighted here, which means that it's going to live somewhere to the left of 1.29. Which means then that my p-value is going to live somewhere to the left over here. And actually, there's one other piece of information that we forgot to get. Remember, we need to make the determination, do we have a one-tail test or a two-tail test? And we can look back at our alternative hypothesis to make that determination. So let me actually hop back really quickly. We said we were doing a two-tailed test because we said not equal to 0. Remember, less than or greater than for your alternative hypothesis means we're doing a one-tailed test. Not equal to means we're doing a two-tailed test. So we're doing a two-tailed test, which means we're going to be looking at that row for our probability. We're looking at this row right here. And since my test statistic lives somewhere to the right of 1.29, that means that my p-value is going to live somewhere over here to the left of 0.2. And if I look at what happens as I move from the right to the left, 0.01 to 0.02 to 0.05, each time I move from the right to the left, my p-value is increasing. It's getting bigger, which means all I can say at the end of this process is that my p-value is going to be greater than 0.2. So my approximation for my p-value is that it is greater than 0.2. So let me hop back over to my problem. So all of this is to say that the p-value is greater than positive 0.2. So that's my approximation for my p-value, and then I'll compare that number against my alpha. We said up here alpha was 0.05. So again, I'll ask the question at the end of this problem, is the p-value less than alpha? So the p-value is greater than 0.2. Alpha, of course, is 0.05. So no, the p-value is not less than or equal to alpha. So because it is not less than or equal to, that means that we do not reject the null hypothesis H0. And if we do not reject H0, that means that there is not enough evidence to support our claim here, our alternative hypothesis. So there is not enough evidence to support that there is a difference and if we need to look back at the language that's used in the problem, I oftentimes think that that's the best way to interpret these problems, just use that same language that they use in the problem. There is a difference between the average reading and writing scores. So that there is a difference between the average reading and writing scores. So hopefully this process felt pretty familiar to the hypothesis testing steps that we were doing in the last section, because they are basically the same. We've made some very minor tweaks to our formulas here and there, but overall it's the exact same process that we've seen. We just have to interpret this as, oh, we're working with a difference data set. We're talking about the difference between two averages rather than just one single proportion, or excuse me, one single average, which we were talking about in the last section.